Okay, now today we're going to do section 3.2. So first, let's look at the text. Scan the book. Let's see, hold it a little closer. Actually, I think we already did this part, but I'm going to do this anyway. Okay. All right, next, page 94, 95. Let's see, a little closer. Okay, and then a little closer on top and a little closer on the bottom. All right. Okay, last two pages. Let's see, the first, the full page, a little closer. Okay, and then, oops, the top. And the bottom. Okay, that's should be it. All right, now that we are ready to start, but before that, I want to remind you some of the stuff from Calculus 3 that, okay, now first, the distance formula, the distance between a plane and a point, okay, is the vector it's the vector dot the plane's normal, okay, divided by normal itself. Please look at this and go into detail more. Is this thing focusing? Well, whatever. Maybe if I pull back a little bit. Well, anyway, so this is the formula, all right. And next, the scalar equation of a plane is, of course, written like this, where n is equal to n is the normal of the plane, and is given as ABC, and that happens to be a coefficient of the variables x, y, and z. Okay, so these two you do need to know for this section. It's not going to talk about it, but it's going to quote it, like you already know this. Next, the definition of the unit tangent vector is defined as r prime t over r prime t's magnitude, being that it's a unit tangent, and the r is the position vector, which in our book is called x. Okay, and really calling it x kind of is inconvenient because we have the position vector x, right? Then we have the cross product, and then we had I don't even the third thing. I don't remember what it was. But anyway, it's just not convenient to have so many x's in there. So the calculus book, the old calculus book calls it the R, which to me seems better. But either way, so next we are going to look at the definition of, remember what is this? The principal unit normal vector, okay? That's defined as n, and remember n is defined as t primed, the derivative of t over its magnitude. Now notice that that's harder to do than it sounds, because that is t prime isn't simply r primed. Okay, you don't just take the derivative of r prime and call it done, because t prime is taking derivative with respect to the variable t, which means you have to do the quotient rule, because that stuff at the bottom, the normal, you also have to take derivative of that thing as well, because that's a function of a t as well. So you end up doing the quotient rule, which gives you a giant headache, but that's the way it is. Now, next we have, of course, the binormal, and and this part you don't have to remember, okay? This part is also harder to remember, you know, the unit normal, the binormal, what was it? I just want to remind you that we did this at one point, and if you don't remember, that's fine, because we're going to develop these two things from the ground up. But I do want to show you why it might look familiar. Okay, now as I mentioned earlier, t prime is not easy to calculate. Okay, and to calculate n, of course, you have to do t prime. That's why the old calculus book says this sentence, which I quoted here: the principal unit normal vector, this thing, can be challenging to calculate. Okay, no kidding. So I just show it to you so just know that to do that, you have to actually take the derivative of the denominator as well. So and then next thing. Next thing I want to mention the various derivative properties, again from Calculus 3. Now, right now the book does expect you to know some of the, all of these things basically. So, so please review them. And that is mostly is the same stuff, right? And specifically, I want you to focus on principle 3. What that is, if you take the derivative of a function and a vector, that is a scalar function and a vector, then it follows the product rule, okay? The way you would expect. And of course, the dot product and the cross product both follow the product rule, with one careful idea is that the cross product, you can't flip it around, because cross product doesn't flip. If you flip, you have to put in a negative sign or something, whereas the dot product does turn okay. And of course, multiplying by a scalar product, you can totally turn it. And then there's an interesting point at the bottom that I've since forgotten. That is, if r of t dot r of t equal to a constant, then r of t dot r prime of t equal to 0. That's something from Calculus 3 that you might have forgotten. And I just want to mention that because I think that might come in handy in this section. Anyway, these are all the things from Calculus 3 that I want you to remember, or sort of pay a little bit attention to. If you don't have to memorize it. If during this video lesson you forget one of these, you know where to look them up. And then I also want you to look at the book itself. You don't have to flip there. I just want to show it to you real quick. First, page 73, okay, there is a theorem 3 on page 73, which says something like, if x prime, x double prime, x triple prime in determinant form is identically 0, and then some other cross product is not 0, then this x is going to be a plane curve. That's going to matter in one of the homework problems. And the next thing I want you to look at is page 90, which we just did, okay? Page 90 has two theorems. I just want to remind you real quick. 90 theorem 1, which says that the parameter t is the arc length if x prime t is identically 1. Okay, that's good enough. Next, we theorem 2, which says that the unit tangent vector is x prime of s. Okay, and also notice this part. That is x prime of s, which is dx by ds, is also dx by dt divided by its own magnitude, which is why it's a unit tangent vectors. All right, so we already had that, so we can so file that away in the corner of your memory while we now start considering the this section. So on page 92, it says the idea of the osculating plane, which a similar idea has been taught in Calculus 3, but we're not going to care about that and just read this thing as it says. The tangent plane to a space curve, okay, is something that contains the tangent at that point to the tangent to the curve. Now, one of these planes might be closer to the curve than another, and that plane is called the osculating plane. And we will give it, what does close mean? Well, we'll give it a better definition later, okay? But that's just the idea, is that the osculating plane is the plane that's somehow close to the curve. It touches it, but also close, or something. But you will see more of that in a moment. So let's look at the next page, page 93, where we have the so-called zero order of contact. What that means is, let's say phi of t is continuous to the nth degree, Cn, then phi of t has a zero of order n at some point if phi of t equal to the kth derivative, okay, all equal to 0 up to n, okay? The only thing that isn't 0 is phi of n at t is 0 is not 0. Then we say that phi of t has a 0 of order n, because the n is the first time that it's no longer 0. Now, if that is the case, well, let's consider an example. Now, think about this yourself for a moment, okay? Sine of t have a 0 of order 1. And you do the sine prime and then figure out when is it not 0, right? 1 minus cosine t has a 0 of order 2. Both of them are evaluated at t equal to 0. So please do that in your head real quick and confirm that that is the case. Now, next sentence is, by use of the Taylor theorem with Lagrange remainder, we can show that phi of t has a 0 of order n, where if and only if the limit of phi of t divided by that t minus t is 0 to the power n equals to a, where a will not be 0. Now, it can be shown that is true, so what are you supposed to do? Let's see you show it, okay? And now I have done it myself, but please show it yourself as well. Now, here's what I did, okay? Applying Taylor's theorem with just one variable on page 43 and the remainder theorem on the following page. I copied it down right here, okay? If that looks familiar, because yeah, I'm pretty sure I got it right. Now, so assuming that this thing has the order of n, right? Which means phi of k, if phi of t has 0 of order n, that means anything less than n, phi k of t 0 is equal to 0. All right, so which means that in this summation symbol, all the rest of the stuff besides n are going to be 0. So we only have left one thing. In the meantime, then the Lagrange remainder is equal to this thing. I write down the big T. Big T is some value between t and t0, according to the definition of remainder, and so on, okay? And you have n plus 1 up here. And so the limit of phi of t, as you divide by t minus t0 over n, will be, so that thing got divided out, so you got phi n of t0 over n prime. n factorial, which is not 0 because we already said that phi n to the of t0 is not 0. So a is not 0, whereas the other thing, it has a t n plus 1 power, dividing t minus t0 to the power n, you still got 1 left, so as the limit of t approach t0, this chunk will go to 0. So then that's how that limit works. All right, so please do that yourself as well. Next, let's look at definition 3, where it says a curve in a plane have contact of order n and at some common point x of t of 0 if and only if the distance phi from a point of the curve to the plane, phi of t, that is, so phi of t is defined as the distance from any point on the curve to the plane, then has a 0 of order n plus 1, and then the contact of order n, well, let me put it this way. Okay, the curve has contact, the curve in the plane has contact of order n if the distance phi of t from the point t on the curve to the plane has a 0 of order n plus 1. Okay, in other words, phi of t has to have n zeros to be called contact of order n. And this is slightly convoluted because one of them says n and the other one says n plus 1, but if you look at it carefully, it will make sense eventually. Anyway, so then we also say that the contact is of order greater than n if phi of k of t at 0 is equal to 0 for all the way up to n plus 1. And there is a reason for that. So please read the details. There's some details to take care of. So, and so that what we end up going to say is the contact sometimes is that contact is of order greater than n. We can't precisely nail it down because of certain logical technicalities that we can't overcome. Okay, so so please think about this until you get the details worked out, and I will move on to example A. The example A says we're going to find the order of contact between the helix and some plane. Now, what was the order of contact we just said? It is the distance, okay, from a point, the distance formula from the point of curve to the plane, and we have to take its derivative and see how many zeros we get. That is, how many of the how many of the second, third, fourth order derivatives are 0, and then that order will be called the order of contact. All right. So example A, having said that, we are going to calculate various things, okay? First, we need to figure out the distance between the point and the plane, which I have, let's see, okay? I have it written down here. The distance is the 2 points, okay? The point on the curve and the point on the plane that we think, the plane that defines the plane, let's see, that would be the normal vector of the plane, all right, which in this case, it happens to be 0, 1, and -1 because the plane end up being that, okay? So then phi of s, let me see, what does it say the plane is? Yeah, the plane is called x2 equal to x3. If you write it in the standard form, that would be 0, over here, 0x1 plus x2 minus x3 equal to 0, which means the plane's normal is called 0, 1, -1. So then phi of s, as defined by this equation, is the point on, this is the point on the curve, okay, minus the set point, which is 0, 1, 1, which I didn't have, I think, I mean 1, 0, 0, one of those things. Let's see, what does it say? Yeah, 1, 0, 0. See, the point is in your book says 1, 0, 0. And now I can't even see. Yeah, 1, 0, 0. So you just do the subtraction to get QP. This is QP, okay? Dot the normal, and that doesn't matter because we're doing the dot product. I mean, the length of the normal doesn't matter. We're just doing the dot product. So then we, after we evaluate the dot product, we'll calculate what phi of s is. And so then we next will calculate phi prime of s and find out that phi prime of 0 is 0. Then phi double prime of s and find out it is also 0. Then phi triple prime of s and find out it finally is not 0. So then it has 0 order, phi then has 0 order 3 because the third derivative is not 0, but the contact order is 1 less. So the contact order is 2, which is what the book says as well. See, the 0 is of order 3, and then the contact order is 2. So please go do all that details yourself as well. It might look tedious, but it's important to do it to get a feel for this stuff. And so that is that should be that. Next, let's talk about the bottom of page 93, definition 4. Now, a tangent plane to a curve which has contact of order greater than unity, in other words, 2 plus is greater than 1, which means it has to be 2 or more, with the curve is called an osculating plane. All right, so let's turn the page to see what that means exactly. Now let's determine the equation of some of the osculating plane. Okay, first, so in theorem 3, first we'll assume that the x's belong to C2, or the components are at least differentiable to the second degree, and then x prime cross x double prime is not 0. Okay, at the point that we're thinking of. So if that is the case, then the curve has a unique osculating plane. So it doesn't just have an osculating plane, it has a unique one. Why is it so unique? Because it is required to have a 0 of order 2. Okay, 2 or more, which is harder to do, and that's what makes it unique. But that's just a quick explanation. We'll see the proof in a moment. The equation is given by the determinant. That's what that parentheses is. Okay, the determinant of x, big X minus x itself. That's the big X is the running variable for the plane. Okay. The small x is the curve, right? So big X minus small x, then small x primed, then small x double primed, second derivative, and you calculate the determinant, and that equals to 0. Now to see this thing in this fully developed form, so this determinant is actually this thing because it's also evaluated at t0. So the whole thing written out looks like this, and that sounds like kind of a pain. But it's not that bad, okay? So that is that's the equation of the unique osculating plane at for the curve at some point t equal to t0. Now, so to prove that, then first we have to consider the distance formula, which we will call it phi. So let's say we have some plane, right? Here's some plane that we have, and then it is well, it contains the point x of t of 0, right? And its normal is gamma. Fine. So we'll do a phi of t function, which is the distance from the curve, any point on the curve, to this plane right here. Okay. So the distance from any point on the curve to the plane, which is the perpendicular distance, and which is of course the formula is given by this thing that we looked at a little bit earlier, the qp dot n over the magnitude of n. And in this case, then gamma will stand for n. So we get, let's see, yeah, so here it is, phi of t, see, that is q minus p, right? That's qp dot n divided by the magnitude of n. Now, and the next step is that if we multiply this thing to the other side, and don't worry about the plus or minus sign. Anyway, so we have a phi then equals to x prime of t dot gamma. Let's take the derivative of it. So what do we get? Then we get phi prime equals to x prime, etc. Similarly, if we take derivative again, then phi double prime equals to x double prime dot gamma, right? Now, now we already know that from condition 2 or hypothesis 2, that x prime cross x double prime does not equal to 0. Now, if that is the case, that means that means something, because if we set these two things equal to 0, because if they are both, if we set them to be 0, then phi prime and phi double prime will be 0 at this at this point. Okay, and how do we set it to be 0? We'll choose gamma in such a way that both of these values equal to 0. Now, if gamma is chosen that way, you notice that being that these cross products are not 0, these two vectors are not parallel, which means gamma is going to be, but gamma dot them is equal to 0 in both cases, which means gamma's direction is uniquely determined by x prime cross x double prime. Okay, there's only one gamma that satisfies both conditions. And that's why, and that gamma is unique. And furthermore, the gamma, the plane that we found, if we design the gamma that way, then the plane is unique, and it causes the, it also has the order, what was the order called? Contact of order greater than 1, because phi prime and phi double prime, okay, are both 0, because we design gamma this way. Okay, so if phi prime, see, if this is both 0, that means phi prime and phi prime is here, phi double prime here, they are both 0, and therefore this tangent plane has contact of order that's 2 plus, that is, in other words, greater than unity, and therefore it is the unique osculating plane, and given by this particular equation. And because, well, that's the equation that we are going to define gamma with. Now, I have it written down a little more, okay? So we let gamma equals to x prime cross x double prime, because for now, the magnitude of gamma we're not as concerned about, okay? Because we're just looking for the equation of the plane. Then if gamma is the cross product x prime cross x double prime, then this equation, the dot product is equal to 0, which means the dot product of the cross product is 0, which is this determinant is 0, which is what we are looking for. And remember that we did choose gamma to be perpendicular to x prime and x double prime, which is why everything in the theorem works out nicely. So please work through this yourself as well, okay, and make everything come out. And so let's look at the next example, example B, where we're just going to work out the osculating plane following the formula that we're just given. That is, the formula says the osculating plane is this determinant right here, okay, and which is a whole bunch of derivatives we need to calculate. So we have, let's see, example B, we have the point itself, but more importantly, we need to, here's the x's, the x, and then x primed, right? Which you calculate the cosine and sine. It becomes sine and cosine. I have tendency to mess up, but eventually I got myself out of there alive, and write it all down, and then do the determinant, and you end up being, well, being that the plane is x2 equal to x3. Everything kind of worked out nicely. so that's pretty good. Okay, and so that is the osculating plane for some, what is this, helix, right? Give me a second here. Now I plotted this osculating plane to show you. As you notice that the plane, let me first make it a little bigger. So the plane looks something like that. And as you can see, there's a point. Can you see the point? Yeah, there's a point there where we have, let me move over a little bit. All right, so the point is at 1, 0, 0, okay? And there should be a dot there. Yeah, you can barely see, you can see the dot because the point is right on the XY plane, but you can still see it. And the plane goes through the plane touches the dot and the curve in a tangent way, and that is the closest way, is the osculating plane. Now that might not look like very close, but if you turn the angle a little bit, and here's a different angle, and you can see that the plane is getting as close as it can manage to the curve. It touches the curve at the, well, in a sense, the closest way. Anyway, that's just to give you an impression of what the osculating plane looks like. All right, so then did I remember to talk about it? I guess. Anyway, so please do this example yourself, okay? Just yeah, I think I just talked about it, didn't I? So, okay, so next. Section 2.3 on page 95, and we are looking at something called a trihedral. Now the word hedral reminds you of the word tetrahedron, for example, and the trihedral means 3 faces for a good reason. Okay, now let's look at these. Suppose we have the arc length parameterization of a curve. So we have remember the arc length is parameterized with S, okay? That matters. The parameterization with S is more difficult in practice, but talking about it is a lot easier because T can be doing, well, who knows what, whereas S follows along the line. And so let's consider, okay, we are defining 3 things. The 3 things are alpha, which is defined as x prime of S, beta is x double prime of S divided by its own magnitude, and then gamma, which is x prime cross x double prime divided by some magnitude. Now first I want you to notice that alpha, beta, and gamma all have unit of 1. The reason is because x prime of S has unit of 1. We mentioned that earlier on page 90. Okay, that is where alpha is end up being, that is x prime of S is equal to x prime of t divided by its own magnitude. Therefore, it is always a unit vector. And the next thing is that beta is by definition is x double prime dividing by its own magnitude, so it's a unit vector. And finally, gamma is x prime of S cross something divided by its own unit vector. So whereas x prime S is already a unit vector, so when you cross another unit vector, you're going to get another unit vector. Actually, is that true? I'm not sure. Let me think. Actually, it's only true if they're perpendicular, because the cross product is the parallelogram, right? But being that these things will prove that they're perpendicular in a second, so yeah, they have the magnitude of 1. But anyway, the next bunch is a bunch of stuff that we're gonna do. We're gonna have to do. That is. Alpha dot beta equals to 0, okay? Beta dot gamma equals 0, gamma dot alpha equals to 0, and then their own magnitudes, when they dot themselves, they're all 1 because they're all unit vectors. And well, once we prove that the dot product between alpha and beta is equal to 0, then we can show, being that they're perpendicular, then we know that the gamma does have a magnitude of 1. So I should note that. maybe I'll do that later. Anyway, so we're going to prove all this stuff. More importantly, alpha is beta cross gamma, beta is gamma cross alpha, and gamma is alpha cross beta. And lastly, alpha, beta, gamma in determinant form is equal to 1. And how are we going to prove all that? Well, by the hint that they give right after here. It says that first, remember the x prime dot x prime equal to 1. That was in a theorem that was mentioned a little bit earlier on page 90. See, because the magnitude of, let's see, x prime dot x prime equal to 1 is, well, that's because well, actually it's by theorem 2, sorry. Okay, it's theorem 2 says that the unit tangent vector is x prime of s. So then x prime dot x prime is equal to 1 all the time, okay? So which means that here's a neat trick that we're going to use to prove all the stuff. The neat trick says that because x prime dot x prime is always 1, then its derivative with respect to s would be 0, okay? Always. Now if that is the case, then x prime dot x prime taking the derivative, which by the product rule is 2 times x prime dot x double prime, will be identically 0. Okay, and well, this is the product rule, which you get 2 of these things. And anyway, all this, so x prime dot x double prime is always 0. And with that, you're gonna be able to verify all those things up on top, which I have. Now please do that yourself, okay? I have it written down here. First, the alpha, beta, gamma are unit vectors. I should write down that this is only true if if x prime and x double prime is if somebody is perpendicular, okay? And but we will show that it's perpendicular, so we'll be okay. Yeah, right here we did show that they're perpendicular, and therefore the well, anyway, somebody is equal to 1. Anyway, so next we are going to prove, skip over here, and because I messed up. And so here's beta dot gamma, which is proven to be 0 after some manipulation. This is gamma dot alpha equal to 0. Beta cross gamma, after much struggling, end up being equal to alpha. Gamma cross alpha end up being beta. And then alpha cross beta end up being gamma by its definition or something. And then alpha, beta, gamma by some determinant rule is going to be equal to 1. So please do all this stuff yourself, okay? If only refer to my notes if you get stuck or something. Otherwise, it should be fairly good exercise of how to mess with vectors. Vectors are not as intuitive as regular number crunching, so it's good to do this type of thing. All right. So having done that, well, then let's look at continuing. We have, so next, let's look at the comments of what all this stuff is. Now, the alpha, beta, gamma has the same disposition, which in modern way we call it orientation. That is the right-hand rule. The alpha cross beta equals the gamma. Okay, the disposition as the original, as our normal coordinate system. Then they have names for it, the tangent vector, the principal normal vector, and the binormal vector, as we have learned in the past, whether you remember or not. And more interestingly, the 3 faces that we mentioned, the trihedral, is the normal plane, the osculating plane, and the rectifying plane. And each plane, of course, has its normal being the corresponding normal, that corresponding vector alpha, beta, or gamma that's normal to it. So so please read this part yourself, okay? And let's look at example C, where we're gonna do all these stuff. And for the helix of the example A, we have we can crank out all the stuff, the tangent vector, that is alpha, beta, gamma, and all the planes, which I have done right here. So please do it yourself as well. It's just a matter of I don't know, calculating. Okay, here's the original x's. We need x prime, right, and then x double prime. And then with that, we, in this case, s is 0. So with s equals 0, we plug in the alpha, and then beta, and then gamma, calculate all that stuff. And then with that, you're able to crank out the plane. We're going through a set point, okay? The point is 1, 0, 0. So with the normal calculator, then you can do the normal plane, the oscillating plane, and the rectifying planes. Yeah, so please do all this yourself, and we will move on to the next page. Next, let's look at problem, page 96, where now we're going to consider the curve x of t. Now, if we were thinking about x of s, as I mentioned, x of s is much easier to talk about. But now we're going to deal with, but s is a very specific parameterization, it's the arc length, whereas t is just any old thing. Okay, so x of t, we can still calculate alpha, beta, and gamma in a similar way, and which is given here. Now the proof of this will be done in homework problem number 12. So that, which means you're going to be doing that. Okay, so we have come to the end of this section. The homework problems to be done is problems 1 and problem 2. And for problem 2, please graph it. Okay, and then problems 3, 6, 7, 8, 9, 10. For problem 10, please don't do only the 10-3. There's also a 10-4, but I didn't bother doing it. So I'm not expecting you to do it either. So then next, problem 12, 13, and 14. So, and when you're done, I want to talk about all of them. So problem 1 on page 96, we are calculating osculating plane, which means we're going to calculate gamma, right? So the normal. So we go ahead and do that. Okay, for gamma, we need x prime and x double prime. In this case, is in terms of t. So we follow the formula for gamma with parameter t on top of this page. And which should give us some number, which should give us some kind of plane. And that turns out to be correct because we do have the answer at the back of the book for this thing. And then so next, problem number 2, I think is a similar deal, except that now we just have a bunch of symbols. So, but the idea is the same, okay? We need to calculate gamma, so we come up with this stuff. Why do I have ABC? I am not sure. Oh yeah, originally it said ABC, that's why. The original twisted cubic has ABC in it. So then, but we follow the same principle, right? And come up with some stuff and not make any mistakes. And then eventually we will come up with some kind of answer where we have the plane. Now, after I came up with the answer, I tested it with t equal to 0 and let ABC equal to 1. So and then I plotted the result into the computer to make sure that I was right. And then at t equal to 0, I did get the right result, but at t equal to 1, it turns out my answer was wrong, but in such a way that it didn't show at t equal to 0. But at t equal to 1, then it definitely showed up, and I had to find my mistake. I don't know what I did wrong there, but I did something wrong. Anyway, so eventually I corrected my mistake, and then everything looked much better. So let me show you what I graphed. I thought, well, anyway, I thought the osculating plane looked pretty neat, right? As here is the graph where I choose A, B, and C equal to 1. And then see, at 1, 1, 1, where I plotted here, then we have, you notice the plane that comes out to looking pretty good, okay? In fact, the plane looks so stuck to it that it makes you wonder if the curve becomes a plane curve after that. But it doesn't, because if you look at, I don't know, at 10 or something, what is that? I don't know. And some other value, okay? Well, anyway, if you magnify this thing at a different point, you see the other graph here, and you do notice that the curve does eventually get out of there, okay? So if you, that is, zoom out. So the curve does get out, but the osculating plane does seem to be hugging the curve very much at the original point. But it seems to be really stuck in there. It doesn't move. The curve doesn't twist much out of there, but it does eventually happen in this case. It didn't become a plane curve and just go stuck in the plane forever. I just thought that seems pretty nice to see, so which is why I asked you to graph it yourself as well. So that is problem 2. And next, let's consider problem 3, which is, I think, are we doing the same thing? Yeah. For this problem 3, we need to again calculate the osculating plane to some point, any point. So that so we do that again. We are going to calculate gamma, which requires us to do both x prime and x double prime, and then and do a bunch of stuff. Okay, and sometimes with sine and cosine, they vanish themselves, with which then we can come up with a fairly simple answer. And that should be that. Okay, I hope there's no mistake in there, but if there is, it should be a simple one that you can spot easily. So let's move on to the next example. Okay, problem 6, we're supposed to find the order of contact of the phi of t. All right, so we, being there's the order, the phi of t with the xy, with the major planes, their equations are very simple. And phi of t is t3 for xy plane, and then you calculate various things. So in contact order is equal to 2, okay, for xy plane, and then for xc plane it end up being contact order is 1, and then the yz plane order is gonna be 0, and the answer is at the back of the book, so that came out quite easily. Now the next one is problem number 7, which unfortunately isn't near as smooth. Problem number 7, so we have, what are we doing? I think a similar matter. Find the order of contact of the curve with its osculating plane at the point 1, 0, 0. All right, so we are going to find, of course, first, what is the osculating plane? So we're going to find gamma, which means we need to figure out what x prime and stuff, right? Here's x double prime and x prime. And then we're going to calculate gamma, which equals to some, and end up with our plane here, which is fine. And then next, we're going to calculate phi, okay? And the phi, following the phi formula in theorem, or just deduce it yourself, either way. What is the phi formula? I'm talking about this equation right here. That determinant, where's the determinant? Okay, which is, the phi formula, which is, just this thing, right? After you figure out what gamma is, whatever. I don't know that matters. Either way, and because we're just calculating gamma, but either way, we have, we got gamma to come out, which then we calculate the formula for phi, which means something like this, and then it is 0, it is 0 as 0, fine, and then prime is 0, that's good, okay? So we next take the next derivative. All right, then the second derivative, which equals to that thing, and it is still equal to 0, which is good. And then the third derivative is by now I used the derivative calculator. Okay, I ran out of steam, so I used the copy, and then when you use the derivative calculator, you can copy and paste the result and stuff it back in the beginning. I'll try to remember to put the link to the derivative calculator that I use, or you can just look one up. But anyway, so I copy and paste the result in to get the third derivative, which is still 0, and then finally I got the fourth derivative. It was no longer 0, so then the contact order then becomes 3. Okay, and so that is problem 7. Next, let's consider problem 8. That is, show the osculating plane of a plane curve is the curve's plane. Well, all right, that sounds interesting. So I have let x of t is in a plane, okay, being that it's a plane curve, and we'll call it the plane x minus b dot a equal to 0. That's fixed. And then, so then, of course, x of t, if you plug the curve in there, it will satisfy that equation, being that it is completely included in the plane, which means this equation is true, okay? And then, so we'll take the derivative of it, and that which gives us over here the x prime dot a equal to 0. Similarly, x double prime dot a also equal to 0. So that means that that a is perpendicular to x prime and x double prime. Okay, and which means that a has the same direction as gamma, which is x prime cross x double prime, which means a has the same direction as the normal for the osculating plane, which means the two planes are the same because they are the parallel and they go through the same point. Okay, so they must be the same plane. So that is why the osculating plane of a plane curve is the curve's plane. So next, let's consider problem number 9. Problem number 9 is, let me find it. I had a bit of a struggle working on problem number 9, but eventually I finally got it to come out. So problem number 9, first let's read what it says. It says the proof that if a curve whose all of whose osculating planes are parallel to a fixed plane, then it has to be a plane curve. Okay, that is an interesting concept. So let's look at this. Now, if all osculating planes are parallel, then of course that means their normals are fixed in direction. That is, they might be different in width and stuff. I'm not talking about a unit normal. I'm just talking about each plane's normal pointing in the same direction. Okay, so then we'll call that direction W, such that when you have x prime cross x double prime will be equal to, which is the gamma, right? For each s, we are parameterizing this thing with s, okay, x of s. And so the cross product at each point s will be, which is gamma at the s, will be equal to some scalar function times the vector w, which points to the constant direction where this cross product is pointing. All right. So as a result, let's say let y of s equal to the cross product x prime s cross x double prime s. Then y prime, if we take the derivative of it, and which applies the derivative of the cross product, which we apply the product rule for the cross product, and it end up being x prime cross x triple prime, and that will be equal to taking derivative of the other side will be f prime of s, because w is a constant. Okay, so the f prime is the only thing that gets taken derivative. And so next we have that's following the derivative of a vector value that's constant. Okay, so next we have, because x double prime s dot w equal to 0. Now why is that? I have an explanation written on the other side, because x double prime s is beta, okay, in the same direction of beta, except that beta of course normalizes itself, but they have the same direction, whereas w is in the direction of gamma, okay, because w is equal to right here. See, w is in the direction of gamma right here, because this is the direction of gamma. So, and being that beta dot gamma equal to 0, they are perpendicular. That means x double prime is perpendicular to w. That is, the dot product has to be 0. And so we plug it in, which means x double prime dot x prime cross x triple prime, this thing right here, has to be identically 0 for each s. And then because of that, then I'll put it another way, that is x prime, x double prime, x triple prime, the determinant is identically 0. Therefore, this x of s is a plane curve by theorem 3 of page 73, which please look that up yourself and to see that. We have, I don't remember us ever using that theorem to this purpose, that is, in the sense of actually showing something is a plane curve. But it seems to work out nicely, okay? So that is my proof for it. So the idea, I got this idea of taking the derivative of y setting y as equal to that and also taking the derivative. I also got that from the proof of theorem 3 on page 73. So it should work out okay. So that's that. Next, let's look at problem 10. Now, problem 10 is just a matter of doing algebra, okay, a huge amount of it. And if you don't mess up, then everything will be okay. And so let's do that. What was problem 10 again? Let me see. It says we're going to find alpha, beta, gamma. All right. So let's do that. So I only want to do the problem 10.3, which is easier. And even then, I was making mistakes, and unfortunately. But anyway, I was able to bail myself out after many various mistakes and was able to get the right answer. It's just a matter of following the definition, okay, and doing all the derivatives, and let's not make any mistakes. And once you do that, then everything comes out okay. What's happening here is I calculated alpha, and then I calculated gamma. Those are the easy ones. And then I calculated beta down here. Okay, and then alpha and gamma are pretty easy to do. Beta is the most complicated answer. So to make sure, I calculate beta in two different ways. The easy way being the gamma cross alpha, and I also followed the book's formula, the hard way, which did come out with the same solution once I found my mistake. So that is problem 10. So next, let's look at problem 12. Prove the formulas on top of the page. And the first one's easy enough, okay? Alpha is x prime over its magnitude, which was given before, okay? We already been through this on page, whatever this is, page 90. See, page 90 at the bottom, it already said so. So that's done. Now, beta is the hard part, okay? I had some trouble trying to get it to come out, but eventually I made it. So what happened is that what I did is I let y of t equals to x of s of t. That is, the first x is x of s, right, parameterized with s, and the second one is parameterized with t. So to tell the difference, I decided to call y of t x of s of t with s plugged in there. That is s in terms of t plugged in there, so that to be able to tell the difference. But then I sort of forgot about that, and then sometimes I write down x of t as well. But remember, x of t means a y of t, or x of s of t. So anyway, with that, I was able to find remember the y prime of t. Being that y of t is x of s of t, then y prime, the magnitude then is equal to x prime of t, which is ds by dt. Okay, so then we calculate all the stuff. Okay, apply the y prime of t is x prime of s, then times ds by dt, right? And then we calculate y double prime, which then we are going to be, which then we can isolate x double prime of s, which we need because beta is given as x double prime of s, and we need to somehow pull the t out of it. So then, x double prime of s, that looks okay, except that we do need x squared, d squared s by dt squared, okay, based on this formula. So we're going to calculate that, which is the derivative of the magnitude of x prime of t with respect to t. So let's write the whole thing out, okay, which equals to that. And then, so the second derivative end up being this thing by the time you're done with it. And now remembering, so at this point, I decided to put x prime of t as y of t, y prime of t to avoid confusion. So then I have y in there. And then, so what we have is, so anything in y is x in terms of t, and x is parameterized in terms of s. All right. So then we have, at least I think it is. But anyway, so we have, so x double prime of t is y double prime of t. So then we have this situation coming up. Yeah, no, I think this is of t. I didn't write it out clearly enough, but I think it's clear from the context. Anyway, so if you keep going, then eventually we calculate x double prime of s to be a fixed formula, which means beta, which is dividing by its magnitude, will be equal to what it's supposed to be, as the formula in the book shows, which is, I believe, this thing right here that translates into the formula in the book, okay, which I did not write down, but it's close enough. So the formula in the book that we're trying to show by the triple cross product, okay, from the triple cross product, this thing is just the cross product of the three things at the bottom in some way, all right? So so that's how I came up with it. I didn't write it out. Well, I guess that's fine. And so that's how beta was taken care of. And finally, gamma is, once we calculate what beta is, which is that thing, then we do gamma, and that by the triple cross product rule again, and something became 0, and then we again end up eventually this. Now we already know the gamma is a unit vector, so we know that once we got the direction, then we just divide it by whatever is on top and the magnitude, and that should give us what gamma is. And then, yeah, this is a small remark that I make for some earlier calculations that I didn't mention. But anyway, so that is how that stuff is proved. As you can see, it's not a short process, okay? But with some patience, it can be done. Next, let's consider problem 13. We have, we're just finding the order of contact of some curve, given curve to some given plane at some given point, and asking, is this plane, is this thing osculating? So let's do a bunch of calculations, okay? After following the formula and get a bunch of calculations out, we write down the formula for phi, the distance formula, and then by then I decided to use a calculator to calculate all the derivatives, and by the time I got to the third derivative, it was no longer 0, but at least it made it to order 2, therefore it is an osculating plane, and that's problem 13. Next, let's look at problem 14, where we have an unusual situation where x prime cross x double prime is 0. Okay, this is referring to the theorem 3 on page 94. And so, however, the x prime cross x triple prime is not 0. And then we can then we're supposed to prove, first thing is that every tangent plane is osculating. Okay, that is the first thing we need to prove. So to do that, we have let's say we have a tangent plane. Okay, and then it contains that vector, so that contains the tangent alpha. And while all planes containing tangent alpha must have so we have a vector n, okay, in the direction of alpha, such as that all planes containing x prime at t0 at x of t0, then it has the dot product equal to 0. That is, equation 1 holds. Any plane that has this situation, then it contains that, that is, this plane contains all vector v at x t0, where v dot n is equal to 0. Okay, and such a plane that well, anyway, so having said that, then we calculate the distance formula with remembering that this situation holds, and then phi prime of then we can calculate phi prime, which is equal to 0 at I think t is equal to 0 in this case. All right, which is fine. And phi double prime is also equal to 0. That's because of this condition. When the cross product is 0, then those two things must be parallel. Okay, unless one of them is 0, but either way, n is perpendicular and this equation equals to 0. So as a result, then phi of t then has a contact of being the phi prime is equal to 0, then phi of t then has contact of order bigger than 1, therefore that tangent plane is osculating. And then the second part of the story, then we're going to consider the proof of on page 94. what happens is that with the situation given, the x prime cross x double prime is equal to 0, but crossing triple prime is not 0. So then remembering that x prime then therefore must be parallel to x double prime, then we borrow the formula from the proof of page 94. Okay, I wrote it down here, and then we'll define gamma as perpendicular to both x prime and x triple prime. Using the same argument there, then I can show that there therefore is a unique, and gamma is defined as x prime cross x triple prime. Where is it? Did I write that down? Yeah, right there. And we'll call that gamma. So by the same logic then, gamma defines the plane of the closest contact. So that's the osculating plane that is the very closest, and is therefore, and is also unique. And that marks the end of this section.